what's this Lebesgue measure of iron? What's iron? Iron is a semi-closed interval. Its Lebesgue measure is equal to its length. So this means the length of the interval a to b plus 1 by n, it decreases to Lebesgue outer measure of I. Lebesgue outer measure of I. So that means that implies what's the length of this? It is b plus 1 by n minus a. It increases to Lebesgue outer measure of I. But what's the limit of this? It's b minus a. So in other words, it means that Lebesgue outer measure of I is equal to b minus a. That's equal to length of I. That proves the case 1. Now we prove case 2nd. Case 2nd. So let's do case 2nd here. Suppose if I is a closed interval, not closed, let's take open interval. I is equal to open interval. Here we define In is equal to, let's define In is equal to I can write this a minus 1 by n to b is it increasing or decreasing sequence? So for n equal to 1, it's a minus 1. So let me explain it here. It's a, it's p. For n equal to 1, it's from a minus 1. Suppose a minus 1 is here. For n equal to 2, it is from a minus 1 by 2. So it will be from this space, from this set, then a minus 1 by 3 is from that minus 4, minus 5, then 0. So it's a decreasing sequence actually. It's a decreasing sequence. It decreases. And you can see that the intersection is intersection is not the open. Intersection is a closed interval. So let me write here. This a plus 1 by n. Let's start this a plus 1 by n. Let's take a plus 1 by n. So then you can see this. This is a, this is b, and for n equal to 1, it's a plus 1. So suppose a plus 1 is here somewhere here. It may be here. It hardly matters. A plus 1, then a plus 1 by 2, a plus 1 by 3, a plus 1 by 4. So it's actually increasing sequence. So first it's a plus 1 to b, second it's a plus 1 by 2 to b. So it's an increasing sequence, and its union is equal to its union never contain a, I think, because every member is less than a, greater than a. So does this union is the member of okay. So you have to check this. Then In is an increasing sequence of measurable sets because they are semi-closed intervals, and the union ion, you have to check this, it's equal to an open interval AB. Open interval A, B. Yes. A plus 1 by n. So one thing is trivial, that this if I choose any member in the union, then that member lies between A and B, therefore it's subset of AB. Subset of AB. And conversely, if you choose any member of the open interval, then it is inserted. Oh, okay, it's done. It's this union is equal to AB. You can easily verify this. So if I choose any member from this union, let's choose X in the union ion. So then X belongs to ion for certain I. So it's suppose an ion means A plus 1 by n to B. So this means A is less than X less than B. So which implies X belongs to the open interval A, B. So that's clear, this one. So whenever X is in the union, X belongs to the open interval A, B. And on the other way, if X lies between A and B, then I can choose n so large such that A plus 1 by n is less than X less than B, by choosing n so large. So it means that here this is this means that X belongs to A plus 1 by n to B. So which implies X belongs to the semi-closed interval A plus 1 by n to B also. So whenever X is in the interval, it belongs to certain semi-closed interval. Therefore, it is in the union. So that means this union is equal to AB. So therefore, by previous theorem, thus this ion increasing sequence, its union is AB. Thus ion increases to AB, and AB is Lebesgue measurable. And one more thing is that limit of Lebesgue outer measure of IN is equal to Lebesgue outer measure of that I is this semi-closed, I is the open interval A. But Lebesgue outer measure of ion, it's a semi-closed interval, it's equal to its length. So that means B minus A minus 1 by n, the limit of this, the limit n approach to infinity, limit of B minus A minus 1 by n is equal to Lebesgue outer measure of I. What's the limit? Limit of B minus A minus 1 by n, it's equal to B minus A. So that means Lebesgue outer measure of I is equal to B minus A, and that's the length of interval. So in this case, it is also done. If I is an open interval AB, then its Lebesgue measurable, and its Lebesgue measure is equal to its length. Now let's choose case third. Let's take case third now. So case third, we can choose. You can choose this case here. I is equal to open on this, closed on this. You can similarly do this proof because the result is already done for the closed intervals. So you had to choose this sequence as in earlier. You had to choose this A plus 1 by n to B. It is the sequence of closed intervals, and we know that the closed intervals are measured. It's already done, and this sequence increases to this semi-closed interval. Therefore, semi-closed interval is also measurable, and the length of this closed interval is equal to the length. This Lebesgue outer measure of the closed interval is equal to its length. It's already done in the first case. So therefore, its Lebesgue outer measure is B minus A minus 1 by n, and the limit of that will increase. Will be the Lebesgue outer measure of that semi-closed interval, but its limit is B minus A, so that is equal to length. So it's an exercise. You can do this. Now let's take a fourth case. There may be more cases. Let's take now this case. So I is equal to A to infinity, unbounded interval. Then I choose this sequence. Choose IN is equal to A plus N. And you can see this, and it's an increasing sequence, and union IN is equal to I. And there are semi-closed intervals, therefore this IN, it increases to I, and it implies Lebesgue outer measure of IN will also increase in Lebesgue outer measure of I. But Lebesgue outer measure of IN is equal to, it's a semi-closed interval, its outer measure is equal to its length, that's A plus N minus A, it's N, which implies N increases to Lebesgue outer measure of I. But what's the limit of N? As N approaching to infinity, it's equal to infinity. So that means Lebesgue outer measure of I is equal to infinity. And it is the same as the length of I, it's already discussed. Length of an unbounded interval is equal to infinity. So another way you take minus infinity to say b, this case can be done similarly. So that proves this result. This that outer measure of every interval is equal to its length, and every interval is measurable. So from this you can conclude that every open subset of R is measurable. Every open subset. So that's an exercise for you. I will give you a hint for that exercise. Show that every open subset of R is Lebesgue measurable solution. So if O is any open subset of R, and then you have already done in the previous course in topology, that every open interval can be written as disjoint union of, every open set can be written as disjoint union of open intervals. So you have to prove this first. Every open subset of R can be written as disjoint union of open intervals, and you know that as done in previous example, each open interval is an open set. So therefore it's a countable union of measurable sets, because each open interval is measurable. Each open interval is measurable, and it is the countable union of measurable sets. And the class of measurable sets is sigma algebra. That's its closed under countable union. Therefore, this countable union of measurable sets is again a measurable set, and that means O is measurable. It also proves that every closed subset of R is measurable, because if F is closed subset of R, then its complement is open, and every open set is measurable. Therefore, F complement is measurable, which implies its whole complement is also measurable, because class of measurable sets is closed under complementation. So that means F is also closed. So every open subset, every closed subset of R is measurable. So in fact, you can prove that that every sigma set is measurable. Every sigma set is measurable. Every sigma set and G delta set is measurable. What is sigma set? So if F is a sigma set, it means that it is countable union of closed sets. And we know that every closed set is measurable, therefore F is also measurable. So that means every sigma set is measurable. Now suppose G is G delta set, then G it's the countable intersection of open sets. By G delta set means it's the countable intersection of open sets, and each open set is measurable, and countable intersection of measurable sets is measurable, therefore G is measurable. So thus every sigma set, every G delta set, they are all measurable sets. So thank you.